Yeah, decoder circuits. So these decoders have just opposite of encoders. We already seen. Decoder have n inputs and maximum 2 power n outputs. 2 power n outputs. Okay, output line. So one of these output will be active high. So in encoder, one of the input will be active high. No. So in the decoder, one of the output will be active high. Active high. Okay. Okay. Active high. So this is just a block diagram. If you see the block diagram, so block diagram for the decoder circuit. So you have n inputs and 2 power n outputs. Okay, decoder. So you have n inputs. So n input lines. These are the n input lines. And one more enable pin is there. Let us take this is enable pin. And next you have 2 power n output lines. 2 power n output lines. Okay. Suppose if you take n equal to 2, so you have 2 to 4 decoder. Suppose n equal to 3, you have 3 to 8 decoder. N equal to 4, you have 4 to 16 decoder. 16 decoder. Okay. So in this you have like four types of decoders are there that we'll discuss. First is active high enable 2 to 4 decoder. So active high enable 2 to 4 decoder. So active high enable 2 to 4 decoder means you have two inputs are there. Let us take the inputs are A1, A0, A1, A0, and four outputs are there. So let us take the four outputs Y3, Y2, Y1, and Y0.
Y1.
Okay, Y0 are the outputs. Okay, so one of these output will be one for each combination of input. At a time, one output will be one. Okay, depending on the combination, one output will be one. Okay, so if you see the block diagram, so this is 2 to 4, 2 to 4 decoder,
Decoder.
2 to 4 decoder. Two inputs are there, A1 and A0, and enable pin. Enable pin is active. So suppose any signal is there, so directly you are giving means that this is active high. This is nothing but active high. So when it is that means active high means when E equal to 1, this will be in active state, and when E equal to 0, this is deactive state. Okay, this is nothing but
The
active high.
decoder will be off.
Decoder will be off. Yeah. Next, so this is active low. When you are giving the bubble, active low. Active low. Active low means when E equal to 0, this will be active, and E equal to 1, and this is decoder will be off to or deactive state. Okay. So there are two types are there. Now we are discussing about active high enable 2 to 4 decoder. Okay. So how many outputs are there? Four outputs are there. These are Y3, Y2, Y1, and Y0. Okay. So here you have the truth table, enable pin, and the inputs A1, A0, and outputs are Y3, Y2, Y1, and Y0. Okay. So so if you see, enable pin is 0. Whatever may be A1 and A0. Okay, the output will be what? Zeros only.
Zero.
Output will be zero only. Okay, when enable pin is 1, when it is a 0 0, y naught will be 1, remaining all are zeros.
Zero.
Okay, and enable pin is 1, y naught, a1 a naught are 0 1, Y1 will be 1. Okay. Enable pin is 1, 1 0. Y2 will be 1. Enable pin is 1, 1 1. Y3 will be 1. At a time, any one of the input will be 1. At a time, any one of the input will be 1. Okay. So so here if you see what is Y naught? Y naught equal to enable pin A1 bar, A naught bar. Okay. What is Y1? E, A1 bar, A
A
naught.
A naught.
And Y2 equal to E, A1, A naught bar. And Y3 equal to E, A1. So this is A1, A naught bar. And this is A1, A naught. Okay. So from this you can draw the logic diagram. So that means let us take enable pin, and one more input. This is A1 connected with an inverter. This is A1 bar, and A naught connected with an inverter. So this is A naught bar. So here this is enable pin. Okay. So what is Y3? Enable A1 A0 connected with the AND gate. This is Y3. Okay. Y2 enable A1 A0 bar. A1 A0 bar connected with an AND gate. This is Y2. Okay. Y2. And Y1 enable A1 bar A0 connected with an AND gate. This is Y1. And Y not equal to one second. Y not equal to
A not equal to A1 bar.
Y not equal to what? So enable pin A1 bar,
A naught.
A naught bar connected with an AND gate. Okay. This is Y not. Okay. Is it fine?
Yes, sir.
Okay. Next, active low enable 2 to 4 decoder. Active low enable 2 to 4 decoder. Active low enable means what? So when the enable signal E equal to 0, decoder will be active state. Decoder will be in active state. Okay. So one of this output combination will be 1. So that means if you see the block diagram, so, so 2 to 4 decoder, two inputs are there, A1, A0, and so you are giving through the bubble. Enable is giving through the bubble, and four outputs Y3, Y2, Y1, and Y0. Okay. So if you see the truth table, enable uh, A1, A0, Y3, Y2, Y1, and Y0. So enable pin is 1. Whatever may be the A1 and A0, all the outputs will be 0 only. Okay. And next, enable pin is 0, 0, 1. So 0, 0, 0, 1. Okay. Enable pin is 0, 0, 0, sorry, 0, 0, 0, 1, 0, 0, 1, 0. Okay. Y1 will be 1, and 0, 1, 0. Y2 will be 1, and 0, 1, 1. Y3 will be 1. So what may be the expression? So this is y naught equal to e bar a1 bar a naught bar. Y1 equal to e bar A1 0 1 A1 bar A naught Y2 equal to E bar A1 A naught bar Y3 equal to E bar A1 A naught. Okay, so you can draw the logic diagram. So let us take E input connected with an inverter and A1 connected with an inverter A1 bar. Okay, A1 bar and A naught connected with an inverter. So E bar A1 bar A naught bar A1 bar A naught bar. This is Y naught E bar 0 1 A1 bar A naught connected with an AND gate Y1 E bar 1 second here E bar no sorry E bar yeah this is E bar and E bar A1 A1 A naught bar A1 A naught bar connected with an AND gate Y2 E bar A1 A naught E bar A1 and A naught connected with an AND gate. This is Y3. This is active low enabled 2 to 4 decoder. Is it fine?
Yes, sir.
Okay. Next,
Hmm.
active high and enable high high and active low output decoder 2 to 4 decoder 2 to 4 decoder. So if you see when enable equal to 1 decoder will be active, decoder is active and one of this output will be what one of this output will be 0. Why? Because active low output decoder no active low output decoder. Okay, so coming to the block diagram, so how it will look like means here this is 2 to 4 decoder 2 to 4 decoder so two inputs A1 A naught and enable active high and there will be bubble outside. Okay, this is Y3 Y2 Y1 and Y0. Okay, so like this that will be there and if you come see the truth table E A1 A0 Y3 Y2 Y1 and Y0 when enable equal to 0 whatever may be the inputs the output will be what 1. Okay, when enable equal to 1 0 0 so y0 will be 0 remaining all are 1 and when enable is 1 0 1 y1 will be 0 remaining all are 1 and when enable is 1 1 0 y2 will be 0 remaining all are 1 and 1 1 1 y3 is 0 remaining all are 1. So if you see I want to get the logic expression so for this y not equal to what so y not equal to so actually I'm writing for POS. You remembered or not in this POS you need to write for the max terms. 0 is true form, 1 is complemented form. Okay, so that means this is E bar plus A1 bar A1 E bar plus A1 plus A naught E bar plus A1 plus A naught. A1 plus A naught. Okay. This you can write as, if you apply De Morgan's law, E A1 bar A naught bar, E A1 bar A naught bar, whole bar. Okay. Similarly, Y1 equal to E bar plus A1 plus A naught bar. So this you can write as E A1 bar A naught whole bar. And similarly, Y2 equal to E bar plus A1 bar plus A naught. This is equal to E A1 A naught bar whole bar. Y3 equal to E bar plus A1 bar plus A naught bar. So this you can write as E A1 A naught whole bar. Okay. Is it fine? Do you understood how I am writing?
Yes, sir. Yes, sir.
Okay, that is related to POS only. So I'm writing for the max term. That is not, these are nothing but max terms. So I'm writing applying the De Morgan's law. So I can arrange like this. So if I arrange like this, I can use NAND gates also. Okay, I can use NAND gates. So one is enable pin, and next one is A1
You
and
know, yeah,
connected with an
but
inverter, and A naught connected with an inverter, A naught. Yeah. So Y3 equal to what? E A1 A naught connected with NAND gate. This is Y3. E Y2 A1 A naught bar. A1 A naught bar connected with an AND gate. Y2. Okay. Y1 E A1 bar. A1 bar A naught. A1 bar A naught connected with an AND gate. This is Y1. Okay. Just expand. Next, E, E, what is Y naught? A1 bar, A naught bar, connected with an AND gate. This is Y naught. This is enable high active load output decoder. Okay. Last one is enable low, active
low,
low, active
active
low,
high,
active low
active low.
output
Okay.
decoder. Output 2 to 4 decoder. So enable low means what? When enable equal to 0, decoder will be in active state. Decoder is active. Okay, and one of these output will be one for each combination. One of output is 0 for each combination. Okay, so if you see the block diagram, two inputs, A1 A naught, and enable pin giving through the bubble, active low, and active low output. So output will be given through the bubble, Y3 Y2 Y1 and Y naught. Okay, so this is 2 to 4 decoder, 2 to 4 decoder, and so truth table enable, next A1 A naught, Y3 Y2 Y1 and Y naught. When enable equal to 1, whatever may be the inputs, the output will be 0. Okay, when enable equal to 0 only, the decoder will be active. Okay, 0 0 means what? Sorry, here active low, no, active low means this will be 1.
One.
This will be 1. Yeah, this will be 1. This will be 1. And Y0 will be 0, remaining all are 1. 0 1, Y1 will be 0, remaining all are 1. And 1 0, Y2 will be 0, remaining all are 1. And 1 1, Y3 will be 0, remaining all are 1. Okay, so here if you see, That means same thing here. You need to write for POS, okay, zeros. So this is E plus A1 plus A naught. This you can write as E bar A1 bar A naught bar whole bar whole bar, and this one E plus A1 plus A naught bar. So this is E bar A1 bar A naught whole bar, and this is E plus A1 bar plus A naught. E E bar A1 A naught bar whole bar. E plus A1 bar plus A naught bar. So E B bar A1 A naught whole bar. Okay. So coming to the logic circuit, E E and given through the inverter. This is given through the inverter, and next A1 inverter A naught given through the inverter. Okay. E A1 A naught. What is my first equation? E bar
A,
E bar.
A, hmm,
mm, Let
A1
us take
bar,
Y A1 bar
A
A
naught
naught
bar.
A naught bar connected with an NAND gate. This is Y naught, and E bar A1 bar A naught connected with an NAND gate Y1, and E bar A1 A1 A naught bar connected with an NAND gate Y2, and E bar A1 A naught. This is A1 and A naught connected with an AND gate. This is Y3. Is it fine? Four
Yeah.
gates. Okay, four gates. And coming to 3 to 4 decoder, how it will look like? 3 to 4, 3, sorry, 3 to 8 decoder. 3 to 8 decoder. 3 to 8 decoder means, so how many inputs? 3 inputs and 8 outputs. 8 outputs. One of these output will be 1. Okay, one of this at a time, one of these output will be 1, depending on the combination. Okay, output will be 1. So that means if you see the block diagram, so this is a 3 to 8 decoder. How many inputs? 3 input. Let us take the inputs are X, Y, and Z, and the outputs are 8 outputs. 8 outputs: 0, 1, 2, 3, 4, 5, 6, 7. Okay. So if you see the truth table, X, Y, Z, and outputs D0, D1, D2,
D2,
D3,
D3.
D4,
So,
D5, D6, and D7. So three inputs are there. How many possible combinations?
8.
8 possible combinations. Okay. 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So here D1 will be 1, D0 will be 1, and here D1 will be 1, D2 will be 1, D3 will be 1, and D4 will be 1, and 101 D5 will be 1, and 111 D6 will be 1, and here D7 will be 1. Remaining all are zeros only. Okay.
Hmm.
So next we need to implement higher order decoder by using lower order decoder. So to need to implement higher order decoder, higher order decoder using lower order decoder. So if you see, I want to implement 3 to 8 decoder using 2 to 4 decoder. 2 to 4 decoder. How to implement? First, let us take so 3 to 8 decoders means 3 inputs and 8 outputs. No,
8
first you
output.
take 1 2 to 4 decoder.
Mm.
So this is enable pin, and here A1 is given to 0, and this is one input A2. A2 is given to A0. Okay, and four outputs D0, D1, D2, and D3. These are the four outputs. Again, here two more decoders, same as mux only. Suppose here you are giving dividing uh, 8 by
4.
8 by 4 means 2 you will get, no. So 2 in first second case, second stage. Two decoders in second stage, one decoder in first stage you will get. Okay. So this is given to enable pin, and this D not also is given to enable pin, and A1 and A naught are given to A1 and A naught are given as the input. A1 and A naught are given as the input. This is A1 and A naught. Okay, and four outputs D naught, D1, D2, and D3, and here also four outputs. Uh, so these are D naught, D1, D2, D3. So these are Y naught to so on Y7. Like this you will implement. Is it fine?
Yes, sir.
One more implementation is with inverter you can implement. Suppose let us take two four decoders, two to four decoders, two to four decoders. Here, so two inputs are common. Two inputs are common. Like so, let us take A1 and A naught. These are A1 and A naught. So this is also A1 and A naught. Okay, and one more input directly you are giving to this decoder. This is A2. You are giving through the enable pin. Okay, active high enable pin. Okay, again through the inverter you are giving to this enable pin. One more input. Okay, so here four outputs are there. Here also four outputs are there. So Y naught, Y1, Y2, Y3, Y4, Y5, Y6, and Y7. Okay. So if you observe the truth table of this one, so here you can consider this one is A2, A1, and A naught. Okay. Now you see. So here, so that means when A2 equal to 0, you will get which inputs, which outputs? D naught to 1 second. Here, here.
D naught to D7.
D naught to
Sorry,
D3 you will get.
D4,
D
D3.
naught to D3. D naught to D3. This one you will get. Okay. And when A2 equal to 1, you will get D4 to D7. No?
D7.
D4 to D7 means here. So when A2 equal to when A2 equal to 1, one is directly given, and here 0 is given. So this will be active state and this will be deactive state. No, you are getting these outputs.
These outputs.
Okay, and when A2 equal to 0, okay, so this is deactive state and this will become the active state, and you are getting these outputs. Understood how I am getting through the inverter circuit I can design.
Hmm.
Okay, okay, and next if you want to design 4 to 16 decoder using 2 to 4 decoder. 4 to 16 decoder by using 2 to 4 decoder. Okay. Same thing you can do. 16 by 4. How much you will
4.
get? 4. This will come in the second stage. Okay. Same as DMUX only. 4 by 4. This is equal to 1. This will come in the
1.
first stage.
First stage.
Okay. Okay. So this is a 2 to 4 decoder. 2 to 4 decoder. So two inputs are there. Let us take the inputs are A and B. And one more enable pin is there. Enable pin is there. 0, 1, 2, 3. Okay. So these, so in the second stage, you have decoders, four decoders. These are given to enable pin. These are given to enable pin.
Able to.
Okay, enable pin of each decoder. Okay, this is 2 to 4. 2 to 4. Here inputs are CD. Common inputs will be there. CD, CD, and CD. Common inputs. Common inputs. And here four outputs. This is D0 to D3. And four outputs. D4 to D7. Four outputs. D8 to D11. Four outputs. D12 to D15. Like this, you will design the 4 to 16 decoder using 2 to 4 decoder.
Yes, sir.
Okay. Next, suppose if you want to design full adder using decoder, full adder, full adder using decoder. How to design full adder using decoder? What is sum? Have you remembered? Summation of m of carry out
No, sir. Some of
minterms
mean
1
terms. Yeah.
to 4 7 and 3 5 6 7. This is carry
It's
out. Okay, so that means how to design means just by using 3 to 8 decoder, each output of decoder is one minterm. Okay, one minterm. So see here, so this is a 3 to 8 decoder. 3 to 8 decoder. Let us take the inputs. Let us take the inputs are A, B, and C in. Okay, and output 0 1 2 3
till
4
till 7.
5 6 7. So these are nothing but minterms. Okay, so 1 2 4 7 connected with which gate? Sum of products.
Sum
Product
of
terms
product.
sum together. That means you need to connect to which gate? OR gate.
Target.
You will get sum. Okay, similarly 3 5 6 7. So 3, so 3 5 and 6 6 and 7 connected with an OR gate, you will get a carry out. Is it fine? Like this you can design any combinational circuit by using decoder.
Yes, sir.
Okay, and one more topic is there, 4 bit 4 input priority multiplexer. 4
4-bit
input priority mux multiplexer. 4 input priority mux. Okay, so that means in this 4 input priority mux, highest priority signal gets least logic path. Highest priority signal, priority signal gets least logic path. least logic path. Okay, so that means output of the priority mux is not valid if all the selection lines are zero. Suppose let us take
Zero.
here this is one mux, one d mux. Input is x3. This is having lowest priority, and this can be either 0 or 1. Okay, either 0 or 1. This is d1 and d naught. Again, this is s3, and this is given to one more d mux, one more d mux, sorry, mux. So this is x2, d1, d naught, d1, d naught, s2, and this output given to one more mux, x1, d1, d naught, and s1, and this is given to one more mux d1, d naught, this is y, and s naught. Okay, so x naught is having least priority, sorry, highest
Yes.
priority. X1 is having highest
Highest
priority. Okay,
priority.
highest priority. Suppose if you see y equal to y equal to, so when s not equal to 1, which is connected,
Sir, when S not equal to 1,
which is connected,
X0, like the last
x0,
one.
yeah, x0 is
Hmm.
connected plus. Okay, again, when s not equal to 0, when s1 equal to 1, which is connected,
X1.
x1 is connected, no? So s naught bar s1 x1 plus, again this is 0, when this is 1, which is connected, x2, no? S naught
S2.
bar s1 bar s2 and x2. Okay, again when this is 0, this becomes what, 1 plus s naught bar s1 bar s2 bar s3 and x3. This is the logic expression for priority mux, which is x naught is having highest priority and x3 having least priority.
Lowest.
Okay, is it fine?
Yes, sir.
So with this we completed the combinational circuits. Tomorrow we'll start the sequential circuits.